What is the weight of this box? So we learned that weight is the force of attraction that objects have, that masses have to other masses. So in this case, we have a mass sitting on the Earth, and these two masses interact because of their gravitational fields, and they pull on each other. So we learned to draw free body diagrams and say that there is a force of gravity pulling down on this object. And this is the force of the Earth acting on the box. And we solve for this by multiplying the mass that we're interested in this case, mv for mass of box, multiplied by g, which is the gravitational field of the Earth. So viewing this on a larger scale, we could draw the diagram like this. Here is our planet Earth, which has a mass m sub e. And then we have our box, which for now, I guess let me place that here. So somewhere far away from the Earth. And that's m sub b, the same box that we have here. These two masses are able to interact because they both have gravitational fields. I can draw the gravitational field of the Earth by using this model, where I just draw lines that are pointing towards the Earth. So these lines show me the direction of the force that a mass would experience if placed in this space around the Earth. We know that the magnitude of the gravitational field of the Earth varies depending on the distance from the center of the Earth. So we are very familiar with this location, the surface of the Earth, where the G value is approximately 10 meters per second squared, or 10 newtons per kilogram, as we'll see in a bit. So the distance from the center of the Earth to the surface, of course, is the radius of the Earth. And in the example that we're discussing here, this box is sitting right here on the surface. So now I can plug in values here. Let me rewrite the equation a bit better here. So we're interested in what is the force of gravity, in other words, the weight. So we multiply the two values, the mass of our box, multiplied by the value of the G field that it's in. And so that's going to be the gravitational field of the Earth at the surface. And those values are 4 kilograms multiplied by 10 meters per second squared. And that will give us a value of 40 newtons. So the force of attraction between the Earth and this box is going to be 40 newtons. I'm trying to make a distinction. I'm trying to distinguish between the mass of the box and the weight of the box, because this is something that we tend to confuse. The mass is the inherent property of the object, so it doesn't matter where the mass is located, it's always going to have a mass of 4 kilograms. But depending on how far away it is from the Earth, the force of gravity that it experiences can be different. So right now, the force of gravity on this box, the pulling force of the Earth on this box, is 40 newtons. There is a different value for the gravitational field strength, let's say a distance 2r from the center of the Earth, so out here where this blue dotted line is. The gravitational field intensity is going to be different. Here it might be something like 2.5 meters per second squared. So 1/4 of the intensity at the surface. And we're going to review why that's the case. So this distance here is 2 times the radius of the Earth. And let's say that the intensity or the distance to the box here is 1, 2, I can move it over to here. So I'll move this box over to here. So the box is located at a distance 3 times further away compared to where it is on the surface. And so the field strength 3 times further away is going to be 1/9 the original value. So the G field here might only be something close to, let's just make it 1 for now, 1 meter per second squared. That is the acceleration that this box would experience. So the force at this location, again, if we use the equation Fg equals m times g, it'll be 4 times 1, and we would get a force of 4 newtons. And if the box were placed at this location here, the force of gravity, the weight of the object, would be 4 times 2.5, so it would be 10 newtons. So the further away we are from the Earth, the weaker the gravitational field, and therefore the weaker the gravitational force. So I can write it quickly here. The weight here is equal to 4 kilograms times the field strength, which is 2.5. And we get 10 newtons. And for this location here, it would be force of gravity will be equal to 4 kilograms times the field strength, which is 1 meter per second squared. And that's how we get 4 newtons. So let's review why the gravitational field strength decreases in this way. So in class, we used the example of light, and we wanted to see how does light intensity change as we move further and further away from the source. We started off with a one-dimensional example using a laser, and we measure the intensity of light. Distance is d away from the laser, so we measure the intensity at a distance d, 2d, 3d, and 4d. The intensity we defined as the luminosity over the area, and just to keep things simple, we are going to say that the intensity of light is just based on the number of rays in our model here, and then we divide by the area over which the light spreads out. In the one-dimensional example, the light doesn't really spread out. So if I place light sensors here, to determine the intensity, I can just count the number of rays that we have. And for each case, we're going to have an intensity of 4. So in a laser, where the light rays do not diverge, the light intensity theoretically should not change. But we don't live in a one-dimensional world, and this is not the way light behaves if it's spreading out. So we can move on to a two-dimensional example where that blue dot is my light source, and the light rays diverge along this two-dimensional plane. And I can remove all the extra light rays here because I can treat this as like a flashlight, and the light rays still diverge. And now I can measure the intensity at a distance r, 2r, 3r, and so on. So at a distance r away, all those light rays are going to spread out over the circumference of this circle. And we know that the circumference of a circle, the equation for the circumference is equal to 2 pi r. And if I'm trying to measure the intensity is equal to the luminosity over the area, which is going to be L over 2 pi r. And because everything here is a constant, the luminosity, the amount of light being emitted from the source, and 2 pi is a constant, we can just say that the intensity of the light is proportional to 1 over r in this two-dimensional example. And so as I double the distance away from the light source, the circumference of the circle is doubling. If I triple the distance from the center, the area of this the circumference of the circle is now tripled and then quadrupled and so on. So when I go to measure the intensity using my light sensors, I can measure it here to be 8 in this model. So I can actually count the number of rays that are hitting the sensor. So I can count 1, 2, 3, 4, 5, 6, 7, 8. And no matter where I put this sensor around this circle, on average, I want to get 8 light rays. For the second sensor, which is twice as far away from the source, I should count 4 light rays, 1, 2, 3, 4. Again, you can move it to any location, a distance 2r away, and on average, the intensity will be 4, so it's half the original. Here, I have 1, 2, 3. But on average, the number is going to end up being 2.7 based on the math that we'll see. And the last one, on average, is going to have 2 light rays. So the intensity here is 8 over 1. The intensity here is 8 over 2, 8 over 3, and 8 over 4. And that's what we mean by the intensity being proportional to the distance r. So I can write it again here. We start off with an intensity of 8 over 1, which is 8. And then it goes to 8 over 2, which is 4. 8 over 3, which is 2.7. 8 over 4, which is 2. And I can keep going 8 over 5 and 8 over 6. So I can predict what the intensity should be. This is the way light behaves in a two-dimensional space. But if I had an actual light bulb in real life, the light is going to spread out over the surface area of a sphere. And so here's a diagram showing how the area increases as we propagate outwards. But in this case, the area does not double like we saw with the circumference of a circle. Here we have the surface area of a sphere, and the surface area of a sphere is equal to 4 pi r squared. And so I have a better model shown here with light rays like we had for the two-dimensional example. And if I had to predict what the intensity is going to be, it's going to be equal to the luminosity divided by the surface area over which the light spreads out. And because we're dealing with a sphere, it's going to be 4 pi r squared. L is constant, 4 is constant, pi is constant. So we can say that the intensity is proportional to 1 over r squared. This is the way light behaves in a three-dimensional world. It's also the way gravitational fields behave. And so this is called the inverse square law. And it allows us to predict how things like light and gravity are going to behave. So in this example, I can count the number of rays to predict the intensity of light here. So here, 1, 2, 3, 4, 5, 6, 7, 8, 9. The intensity here is equal to 9. In this example, on average, the intensity is going to be equal to 2. There are 1, 2, 1, 2, 1, 2. And this last one has 3. But I can then take this last R and divide it amongst all 4 panels, and I get something like 2.25. 2.25. Yeah, we'll check that when we do the math in a second. And then for the last one, the intensity on each panel here is going to be approximately just 1. So we start off with 9 rays. So it's going to be 9 over the distance squared. And then we have, so the proportionality is, or the intensity is proportional to 1 over r squared. So for the first one, we have 9 over 1 squared. That gives us an intensity of 9, like you saw here. For the second one, it's going to be 9 over 2 squared. 9 over 4 is 2.5. No, not 2.25, not 2.5. And for the last one, it's 9 over 3 squared. So that's going to be 1. Yeah. And that's what we see here, 2.25 and 1. And so we can then predict at a distance 4r, what will the intensity of light be? And it'll be 9 over 4 squared. So about a half the intensity. All right, here's another diagram that shows the values as we propagate outwards for a light source. If the intensity here is 1, you double the distance, you'll have 1/4 the intensity. You triple the distance, you'll have 1/9 the original intensity. And this is how light behaves, and also how gravity behaves. Okay, so let's look at another example for gravity. So let's say this time I have the Earth over here. And so this is Earth mass ME. And we have, let's say the moon. Let's do the moon, yeah. So this is not going to be to scale. Let's say the moon is all the way out here. So M sub M. And I want to know what is the force of gravity between these two objects. And We're also going to come back and figure out how we get g equals 10 meters per second squared here at the surface of the Earth. So I'm not forgetting about that. I'll come back to it. So the moon here is going to experience a force of gravity towards the Earth because it is in the presence of the Earth, which has a gravitational field around it. And there's a certain value associated with the gravitational field at this location around the Earth. Right, so what is the value for the gravitational field here at the moon? So it's really far away. Well, we need to know what is the value for the mass of the Earth, because that's going to affect how much gravity we have here. We also need to know what is the distance from the Earth all the way out to that location. I should draw it like this, to the moon, to that black dotted line. So this R value is also needed. We can look up these values on the reference table. So the mass of the Earth is 5.98 times 10 to the 24th. We can also write this as 5.98 E24. These two are the same number. Writing it out this way is going to be useful for when we type this into our calculator. It's more efficient and faster to write it out this way. The distance from the Earth to the moon is also on the reference table, and that is the average, the mean distance from Earth to moon is 3.84 times 10 to the 8. Meters. And so the field intensity at this location is going to be based on the mass of the Earth, ME, and we're going to divide by the distance squared, the distance R squared, and then we need to introduce a constant, and that is the universal gravitational constant, capital G. Write it out here. Universal gravitational constant. Capital G, which is equal to 6.67 times 10 to the negative 11 newtons times meter squared over kilogram squared. And this is the proportionality constant needed to come up with our G value. And now when we plug in our values, we'll get G is going to be equal to the universal constant multiplied by the mass of the Earth. Actually, let me give myself some more space here. G is equal to, I can type G actually out here. The mass of the Earth goes here, and then the distance squared goes here. So this number is 6.67 times 10 to the negative 11 newtons times meter squared over kilogram squared. The mass of the Earth is this value here, 5.98 times 10 to the 24 kilograms. And then we divide by the distance squared, 3.84 times 10 to the 8 meters. We can plug these values into our calculator and get the G value at this location near at the moon. And so yeah, let's do that calculation. So we have parentheses 6.67, and then I could do this like it's times 10 and then raised to the power negative 11 and get this value. You see the calculator types it out in this format anyway. So it's a lot easier to do that. I can write 6.67. And then to type in that E value, I go second E negative 11. And then multiply that by the mass of the Earth, which is 5.98 times 10 to the 24. And so this is our numerator. And then we need to divide this all by 3.84 times 10 to the 8 squared. And we get this as our gravitational field intensity all the way out at the moon. It's 0.0027. 0.0027. And let's look at the units now. So the meter squared cancel out with the meter squared over here. This kilogram cancels out with one of the kilograms here. And so we're left with newtons divided by kilograms. So newtons per kilogram. So this is representing the gravitational field strength. You can place any mass there and you can calculate the force of gravity acting on any object. We can even bring our little box here and calculate the force of gravity acting on it here. So let's start with the force of gravity acting on the moon. I just take the mass of the moon and multiply it by the field intensity at that location. So what is the mass of the moon? I can find it here on the reference table. The mass of the moon is 7.35 times 10 to the 22. So 7.35 times 10 to this 22nd power. And then multiply that by 0.0027. And we get that the force of the Earth on the moon is approximately force of gravity of the Earth on the moon is approximately 1.98 times 10 to the 20th newtons. So that's a large force, and you might think, well, this number is really small. How can this number be so big? It's because the mass of the moon is so big. Let's do a similar calculation for the mass on our small 4 kilogram box. So it's going to just be 4 kilograms times 0.0027. So 4, just like before. So instead of the mass of the moon like we have here, we're using just the mass of the tiny box. Then multiply that by 0.0027. And we get a really tiny force there, which is 0.0108 newtons. Again, this value here is describing the field intensity at this location really far away from the Earth. The number that we're used to seeing for gravitational field strength is the intensity here at the surface of the Earth. So let's go ahead and calculate that using the equation that we just learned here. I'll write the equation out again. It's this equation. So what is the field intensity here at the surface of the Earth? Well, it's going to be G is equal to 6.67 times 10 to the negative 11 newtons times meter squared over kilogram squared times the mass of the Earth again, which is 5.98 times 10 to the 24 kilograms, divided by the distance to this location squared. So the distance from the center of the Earth to the surface of the Earth, that is the radius of the Earth. We're going to square it. The radius of the Earth, we saw here, average radius of the Earth, 6.37 times 10 to the 6. 6.37 times 10 to the 6 meters. And again, we're familiar with this value. We know that this number should be approximately 10 newtons per kilogram, or something close to 9.8 or 10 newtons per kilogram. So let's do this calculation. I'm going to go to my calculator and do this quickly. So the universal gravitational constant is 6.67 times 10 to the negative 11, multiplied by the mass of the Earth, which is 5.98 times 10 to the 24th, and then divide by the distance to the surface squared, which we can call the radius of the Earth, 6.37 times 10 to the 6 squared. We have to make sure that we square this value in the denominator. And we get 9.83, very close to the 9.81 value that we usually use. Yeah, but we can just round that up to 10. And that's how we get our G equals 10 newtons per kilogram. So when we place our 4 kilogram box here, to find the force of gravity acting on it, all we did was we multiplied the mass of this box times the gravitational field strength at this location. So we saw that here the force of gravity was 40 newtons, but at a distance of 3.84 times 10 to the 8 meters, we get a really tiny force. Okay, another way to calculate this value directly, let me go back to this force of gravity on the moon. Instead of solving for the field intensity here and then multiplying that by the mass of the moon, we could have just taken this whole thing and multiplied by the mass of the moon. So let me rewrite this here. Yeah, let me get rid of this. So we found that this G value here, G at mass of the Earth times distance to the moon squared, is 0.0027. And then to solve for the force of gravity, what we did is this. So the force of gravity is equal to, the force of gravity on the moon is equal to the mass of the moon, so mass m sub m, multiplied by the gravitational field intensity. And that's how we got this number, right? That was this. So instead of doing that, what we could have done is recognize that this lowercase g is everything inside these parentheses. So I can write that down. It's capital G for the universal constant, multiplied by the mass of the Earth, and then we divide by the distance from the Earth to the moon squared. So we have all of this here is lowercase g, and what we have to do now is multiply by lowercase m for the moon. We get this equation. So the force of gravity between two masses can be solved by using this equation. And this is the equation that we saw in class as the equation for the force of gravity between any two masses. So as long as I know what the two mass values are and I know the distance between them, I can just use this equation directly. But I just wanted to make sure that we all understood that this equation is the same as this equation. So one last thing about this problem is that we can look at this in another way. Instead of thinking about the moon being placed in the Earth's gravitational field, we can think about this as the Earth being placed in the moon's gravitational field. So what does that mean? I can draw the moon and the Earth again, like I had the Earth here, and this is the mass of the Earth, ME, and we drew the moon up here, M sub M. Oh, did I actually write that? M sub M? Yeah, I did. Okay, good. So we said, well, the Earth is creating a gravitational field around itself, and that's what's pulling on the moon. But we could equally say that the moon has a gravitational field around itself, and it is pulling on the Earth. So what is the value for the moon's gravitational field here? We can solve for that by using this equation again. G equals G, mass of the moon, divided by the distance between the two, or from the moon to that dotted line, squared. And we would get a different G value. It's going to be smaller than the value we found for the Earth. Multiply that then by the mass of the Earth, and we will get a force of gravity that the moon is pulling on the Earth with. And that number should still be 1.98 times 10 to the 20th. It's actually the same force. So this is an example of a third law pair. These two forces are the same. And I can show that in a simulation that we have here, a PhET simulation called Gravity in Orbits. And I'll use the Earth and Moon example, and I'll play this simulation. We have the moon here rotating around the Earth, and I can show things like the velocity of the moon. I can show the path that the moon traces. It's shown here as a perfect circle, even though we know it's not really. But I can then also show the forces. And so if I click on forces, you see that there's a force on the Earth and there's a force on the moon. So the force on the moon is always perpendicular to its velocity. So that tells us that there's some kind of circular motion going on here. And we should also expect that, so just how the moon's accelerating, because it's moving in a circular path, and there's a net force acting on it, the Earth also has a net force acting on it. So shouldn't the Earth also be accelerating? And actually it is, but because it has such a large mass compared to the moon, it's difficult to see that acceleration. But if I zoom in and show this grid, we should be able to see that even in the simulation, I'll put my cursor here so we can see that the Earth is actually also kind of wobbling. It's moving also in a small circle. If the Earth had a smaller mass, you would be able to see it moving more. If it had a larger mass, it would not be as obvious, but the Earth also is accelerating due to that force of gravity acting on it. Okay, let's see what else do I have. All right, we're gonna look at some questions here. So here's the equation one more time. Here's the force of gravity, which we also refer to as the weight of the object. R is the distance between the object and not the radius necessarily, though often we can, if we're talking about an object sitting on the surface of the Earth like we have here, then the R value here is equal to the radius, but it's really the distance between the center of the two objects. And that can also bring up a question where, yeah, if we have, let me draw a better circle here. We have the Earth, and we have our box sitting on the Earth like this. Now on this scale, this is a gigantic box, but this is just so we can talk about this together. Here's the center of the Earth. Here is the center of the box. The distance between them, first of all, is not 0 because they're touching each other. When we say the distance between them, we mean the distance between the two centers of masses. So the distance from here to the surface is the radius of the Earth. And you might say, well, what about the distance from the center of the box to the surface? Don't we have to include that as well? Well, we saw that this value here is, yes, it's the radius of the Earth. It's 6.37 times 10 to the 6. So this number here, let me write out here, 6.37 times 10 to the 6. And this value here for the box, let's say this box is the size of a house, so maybe, I don't know, let's make the radius or the distance from the center to the bottom something like 20 meters. This number is so small compared to this number that it's not going to change our final answer. So we can ignore the size of this object and just take the R value to be from the center of the Earth to the surface. So in that case, it is the radius. But if the box was sitting somewhere out here in space, I want to find out what is the force of gravity, then of course I have to find the distance from the center of the Earth to the center of the object. In that case, the distance here is significant. Okay. So R is the distance between these two objects. M1 and M2 are the two masses, and G is the universal gravitational constant, which the value is given to us as the first constant on the reference table. So we have a list of physical constants, and the first one is the universal gravitational constant value, and the magnitude and the units are shown here. Okay, so here's a sample question. what is the diagram shows two bowling balls A and B, each having a mass of 7 kilograms, placed 2 meters apart. What is the magnitude of the gravitational force exerted by ball A on ball B? And yeah, you can pause the video if you like to try it out. It's a multiple choice question. But here's the solution. We would say the force of gravity is equal to G m1 m2 divided by r squared. This equation can also be written, by the way, as just a single numerator like this in case you're confused. m1 m2 all over r squared. And so we would get 6.67 times 10 to the negative 11 newtons times meter squared over kilogram squared times 7 kilograms for the first mass, 7 kilograms for the second mass. And then we divide everything by the distance between them squared. So here's the center of the first bowling ball, the center of the second bowling ball. And so the distance between them is just 2 meters. We square that number. So let's plug this into our calculator. So we have our universal constant, 6.67 times 10 to the negative 11. And then multiplied by 7 for the first mass and 7 for the second mass. And then we divide by 2 squared. And the answer should be 8.17 times 10 to the negative 10. And that's going to be this answer number 3. Next question. As a meteor moves from a distance of 16 Earth radii to a distance of 2 Earth radii from the center of the Earth, the magnitude of the gravitational force between the meteor and the Earth becomes, so let's say the Earth is here, and there is a meteor that starts off 16 Earth radii away, so somewhere out here, here's our meteor. And then it's going to become 2 Earth radii away, so it's then going to be here. When the meteor is really far away, we should expect there to be a very small force of gravity. And when it's close to the Earth, it's going to be a much larger force of gravity. And we want to know by how much does this force increase? So I call this Fg1, and I call this Fg2. Essentially, what is the ratio between Fg2 to Fg1? So at Fg2, yeah, so we want to know what is Fg2 over Fg1. Fg2, the force of gravity at this location, is going to be equal to G, mass of the Earth times mass of the meteor, divided by the distance squared. So this is the important part, the distance squared. Let me also set up here for Fg1, the force of gravity between the Earth and the meteor when it's 16 Earth radii away. It's going to look very similar. It's going to be the constant. Mass of the Earth, mass of the meteor, divided by that distance squared. So the distance here was 2 Earth radii, so 2 Earth radii. And the distance for Fg1 is 16 Earth radii. And the answer to this is going to be the solution to our problem. So we can just cancel out everything here. That's the same on both sides of the equation. Even RE squared is going to cancel out. So the answer is going to be 1 over 2 squared divided by 1 over 16 squared. And that is going to be 1 over 2 squared divided by 1 over 16 squared. And the answer is 64. The answer is going to be 64 times as great, so answer is 3. And I think that's it.